Welcome back to the deep dive. So you've handed us the blueprint for what feels like, well, Chemical Control Chapter 8 of the ASA level chemistry text.
It really is.
And this material isn't just about memorizing definitions. It's about giving you the quantitative tools to predict, manipulate, and really dominate how chemical reactions behave.
Exactly. Our mission today is to distill this massive chapter into its core insights. We're moving from the qualitative rules of how reactions shift, that's the Chatelier's principle, to the precise mathematics of equilibrium constants, your Kc and Kp.
Right.
We'll show you how chemists apply these rules in billion-dollar industrial processes, and then we'll shift gears entirely to look at how these same equilibrium principles govern the fundamentals of acids and bases in solution.
So think of this deep dive as your structured shortcut. By the end, you won't just know the definitions, you'll, I think, understand the decision-making process behind controlling chemical outcomes. Let's unpack this reversible world, starting with the dance itself. Dynamic equilibrium.
Okay, so when we talk about equilibrium, we're really talking about reversible reactions, where the products can react to reform the original reactants.
The classic example is always that copper sulfate, isn't it?
It's the best visual one. You have blue hydrated copper sulfate, you heat it, it loses water, and it becomes white anhydrous copper sulfate.
Then you just add water back, and bam, it reverses. It's blue again.
Exactly. And that double half-arrow symbol you see, the one going both ways, that's the signpost for dynamic equilibrium.
And that's not a static stop sign. It's a dynamic balance with, what, 4 key rules? The first being that it's, well, dynamic. The molecules are always reacting.
Constantly, in both directions. And that leads to the second rule, which is the essential balance. The rate of the forward reaction equals the rate of the backward reaction.
Which is why, and this is the third rule, the concentrations of reactants and products stay constant.
Hold on. That's the point that trips everyone up.
Wait, if the concentrations are constant, does that mean they have to be equal?
No, and that is the absolute key takeaway. Constant does not mean equal. It just means the ratio is stabilized. You could have 10 times more product than reactant, but because they're being made and used up at the same speed, that ratio doesn't change.
Got it. Okay. So the final characteristic is critical for this to even happen. Equilibrium needs a closed system.
Absolutely. If a product, especially a gas, can escape, the reverse reaction can't happen. The system just goes to completion.
And what's fascinating is that this equilibrium position is stable, right? It doesn't matter how you start.
Not at all. You can start with only reactants or only products. Under the same conditions, the system will always adjust itself to reach the exact same equilibrium concentrations.
So equilibrium is stable, but we as chemists want to control it. We want to manipulate it. And that brings us to Le Chatelier's principle, the ultimate rule book.
It's so elegant and simple. Le Chatelier's principle basically says, if you make a change to a system at dynamic equilibrium, the position of equilibrium will shift to minimize or oppose that change.
And we have 3 main control knobs to do this. The first is concentration.
Right. So if I increase the concentration of a reactant, say I add more ethanol to an esterification reaction,
the system immediately panics and shifts to the right to use up that extra ethanol and make more product.
Exactly. And removing a product does the same thing. The system shifts right to replace what you just took away.
Okay, knob number 2, pressure. And this is only for reactions with gases.
Yes, because liquids and solids aren't really compressible. So if you increase the pressure, the system shifts toward the side with fewer moles of gas. It's trying to relieve that stress to make more space.
Like in the Haber process for ammonia synthesis, you've got 4 moles of gas reactants turning into 2 moles of ammonia product. That high pressure is specifically chosen to force the reaction to the right towards that lower mole count.
Precisely. Now, the final knob is temperature. This one is all about the reaction's energy. It's AH.
Okay, so if you increase the temperature,
the system favors the endothermic reaction, tries to absorb that extra heat to cool itself down.
And if you decrease the temperature, it favors the exothermic reaction to generate some heat.
You got it. So for an endothermic reaction, like the decomposition of hydrogen iodide, cranking up the heat drives the reaction forward.
And a quick but really crucial side note here, catalysts, they don't fit into these knobs, do they?
No, they're different. A catalyst increases the rate of the forward and the reverse reactions equally. It just gets you to equilibrium faster.
So it's a speed booster, not a manipulator. It never affects the final position of equilibrium.
Never. That's a critical distinction.
So Le Chatelier's principle lets us predict which way the reaction shifts. But if we want to know how far it shifts, we need numbers. And that's where the equilibrium constant, kchi, comes in.
Right. kCaudy gives us that quantitative measure of the position. It's simply a ratio. The concentrations of products on top, reactants on the bottom, all at equilibrium.
And each one is raised to the power of its stoichiometric coefficient from the balanced equation.
So for a general reaction, say Ma plus Nb goes to Pc plus Qd, the expression is Kc equals C to the power of P times D to the power of Q, all divided by A to the power of M times B to the power of N.
The most important insight here isn't just the formula, though. It's what the final number tells you. What does a large or a small Kc really mean?
Great question. If your Kc is huge, like 10 to the 5 or bigger, that tells you the numerator, the product, is massive compared to the denominator, the reactants. The reaction has basically gone to completion.
And if Kc is tiny, say 10 to the minus 5.
Then the reaction has barely started. You have almost all reactants and very little product. Kc is like the reaction's final report card.
And we have to remember the rule of exclusion. Solids and pure liquids are left out of the Kc expression.
Yes, because their concentrations are effectively constant, so they just get baked into the value of Kc itself.
Now what about the units? That calculation can be a nightmare if you try to memorize the algebra for every single reaction.
Don't memorize it. Just think it through. If you have the same number of moles of products and reactants, all the units cancel out. KCC is unitless.
But if they don't cancel?
You just follow the algebra. If you have, say, 2 moles on top and 3 on the bottom, you'll end up with units of dm cubed per mole.
So the real key to these calculations isn't the final math, it's the setup. It's that logic of initial moles, change, and then equilibrium concentrations.
Absolutely. The setup is everything. You often have to work backward from how much product you made to figure out how much reactant must have been used up.
And finally, a concept we just cannot repeat enough. The value of Kc is only affected by one thing.
Temperature.
Only temperature. Changes in pressure, concentration, adding a catalyst.
None of that changes the value of Kc. It just causes the system to shift its concentrations around until that original Kc ratio is restored.
Okay, so that's Kc for solutions, but for systems that are all gas, we have Kc.
Right, because for gases, it's often much easier to measure pressure than concentration.
Yeah.
So we use Kc, the equilibrium constant, based on partial pressures.
And partial pressure is just the pressure that one specific gas in a mixture is exerting, right?
Exactly. And Dalton's law tells us how to find it. The partial pressure of a gas is its mole fraction multiplied by the total pressure of the system.
The kBond expression looks identical to the kbond, doesn't it?
Structurally, yes. You just use the symbol P for partial pressure instead of the square brackets for concentration. So for the Haber process, it's the partial pressure of ammonia squared divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed.
So the trick in kBond calculations is really that conversion step. You have to find the total number of moles at equilibrium first, then work out the mole fraction for each gas, and then you can find their partial pressures.
That's the sequence. Once you have those individual pressures, you just plug them into the kBond expression.
Let's look at why mastering these rules matters so much. In industry, it seems like it's almost always a battle between yield, what Le Chatelier says you should get, and rate, how fast you can actually get it.
That's the eternal compromise. Take the Haber process. It's exothermic, so Le Chatelier tells you a low temperature will give you the highest yield.
But if the temperature is too low, the reaction is impossibly slow. You'd wait forever.
Exactly. So they use a compromised temperature, around 450 degrees Celsius, to get a decent rate, even if it means sacrificing some of that maximum possible yield.
And this is where the chemical genius comes in. To get around that, they continuously remove the ammonia by cooling it down until it becomes a liquid.
Yes. And because the ammonia product is removed, Le Chatelier's principle dictates that the equilibrium has to shift constantly to the right to try and replace it. It's a clever way to keep the reaction moving forward.
Now let's contrast that with the contact process for making sulfuric acid. This one is also exothermic, and it also favors fewer moles, so high pressure should be good.
It should be. But here's the beautiful practical detail. The Kp for the contact process is naturally so enormous that the reaction is virtually complete even at just above standard atmospheric pressure.
So you don't need to spend millions on expensive, high-pressure equipment.
You don't. The chemistry is already so much in your favor. It's a huge cost saving.
We've seen how industry manipulates gases for profit. Now let's dive into the aqueous world, because equilibrium is just as critical in liquid systems, especially for something as fundamental as acids and bases.
And for this, we use the Brønsted-Lowry theory. An acid is a proton donor, an H+ donor, and a base is a proton acceptor.
And some things, like water, can be both amphoteric.
Right, they can swing both ways depending on what they're mixed with.
Okay, that distinction, strong versus one and concentrated versus dilute, that is the one concept that trips up nearly everyone. Can you give us an analogy to make sure we never mix those two up again?
Let's try. Think of concentration as how many boxing gloves you own. It's just
Okay.
the amount of substance per volume.
Yep.
Strength is about how good those gloves are at actually ionizing and releasing their protons. A strong acid, like HCl, is a fantastic ionizer. It dissociates almost completely in water. The equilibrium is way, way over to the right.
So you get a really high concentration of H plus ions and a very low pH.
Exactly. Now, if you have a weak acid, like ethanoic acid, it's a poor ionizer. It only dissociates partially.
Meaning the equilibrium lies far to the left. You get a low concentration of H plus ions and a much higher pH, even if the starting concentration of the acid was the same.
You've got it. And because strong acids create so many more free-moving ions, we can distinguish them with simple tests. They show much greater electrical conductivity.
They'll have a lower pH.
And they react way faster with metals because there are just so many more H plus ions immediately available to react.
So to monitor these solution reactions, we use indicators, which are actually equilibrium systems themselves, usually weak acids.
Yes, you can represent them as H ion in equilibrium with H plus and in. The acid form, H ion, and the conjugate base form, in, have different colors. And the color change happens when the pH shifts that equilibrium from one side to the other.
So the real challenge in a titration is picking the right indicator for the job. You're looking at the pH titration curve, specifically that steep vertical section where neutralization happens.
And your indicator must change color precisely within that steep region.
The shape of the curve dictates your choice. A strong acid-strong base titration has a massive, steep drop, and it's centered perfectly at pH 7.
So pretty much any common indicator will work there. The transition window is huge.
But if you titrate a strong acid with a weak base, that steep change happens entirely in the acidic region, maybe pH 3.5 to 7.5.
Right, so you have to choose an indicator that operates in that low pH range, something like methyl orange. If you used phenolphthalein, which changes in the alkaline range, you'd miss the endpoint completely.
And conversely, for a weak acid with a strong base, the steep part is on the alkaline side. So there, phenolphthalein is the perfect choice.
It is. And critically, for a weak acid, weak base titration, there's no sharp change at all. It's just a gradual slope.
Meaning no indicator can accurately pinpoint the endpoint. You just can't do it that way.
Exactly. So we've covered a massive amount of ground here. We started with the definition of dynamic equilibrium in a closed system, then the predictive power of Le Chatelier's principle for concentration, pressure, and temperature.
Then we quantified it with Coursey and Casey, always remembering that only temperature can actually change that value.
And we finished by really hammering home the distinction between the degree of dissociation, that's strength, and the amount of substance, which is concentration, in acid-base systems.
So what does this all really mean? It means you now have the toolkit to not just predict how reactions will go, but to quantify them, whether you're designing a multi-million-dollar chemical plant or just understanding the tiny systems that keep you functioning.
I mean, just reflect on the complexity of the acid-base systems in your own body. Your blood, for instance, maintains a ridiculously tight pH range around 7.4, using buffer systems that are just complex acid-base equilibria.
Wow.
That subtle balancing act, governed by these very precise rules we've just discussed, is literally what's keeping your body from shutting down.
A truly high-stakes application of dynamic equilibrium happening inside all of us right now. Thank you for joining us for this deep dive.